Hi, our final talk for this session is by Wei Zhan, who's speaking about anti-concentration for the unitary Haar measure and applications to random quantum circuits.
Thank you. So this is a joint work with Bill and Soumik. Both are here. And so this is the agenda of this talk, what we are going to cover. We are going to start with a quiz question about random quantum circuits. And following that, we will introduce our contribution in this work and give a brief explanation of the title. And finally, I'll give you one of the many applications of our contribution that allows us to learn random quantum circuits of logarithmic depths in polynomial time. So let's start with the question. Here's the setting. So we have a very simple toy model of random quantum circuits, which is Bergward circuit in one dimension. So we have d layers of gates. Each layer contains independently Haar-random unitaries on two qubits applied on neighboring qubits, alternating in each layer. And the depth of this circuit is d. So one particular property of Bergward circuit is that it kind of scrambles the information. And one way to characterize this scrambling property is to look at the entanglement between one cut of the qubits with another cut. And here we can look at a continuous cut of the qubits represented by A. And we are examining its Remy 2 entropy and look at how it grows with the depth. So it basically roughly grows like the graph here, where it starts off, grows linearly in depth, where we call it, obeys the area law, until the entropy reaches almost the size of the cut, when we say that the entropy is saturated, and then it obeys the volume law. So specifically, we can think of one case where this cut of the qubits consists of only one single qubit. And in this case, the entropy gets saturated almost immediately. And we know that it means that the reduced density matrix on that qubit will get closer and closer to maximally mixed. And the distance from maximally mixed is exponentially small in depth. So that raised the question, can we use this property of the scrambling of this speed of entropy on single qubit to tell the depth of a random quantum circuit? So specifically, let's think of two cases where we want to distinguish between if the circuit has linear depth or if the circuit has logarithmic depth. So to do that, let's think of just looking at one specific output qubit, and we try to test this Remy 2 entropy by doing something like a swap test. And we can observe that the outcome and see if it is close to maximally mixed on that single qubit. If it is close, then we say that the circuit must be of very high depth, and if it is not, then it's of low depth. So the quiz question is that, does this work? So if you think it works, you can raise your hand. If not, okay. I see some raising hands. I also see some shaking heads. So if you think the answer is yes, then unfortunately you might be fooled by expectation. So the thing is that I intentionally being very sloppy about this Remy 2 entropy of a single qubit. This distance with maximum mixed only holds in expectation, or we only know that it holds in expectation. And expectation does not mean typicality. Okay, so you can kind of use Markov to get one direction of the inequalities, but for the other direction of the inequality, that you try to show that it is bounded away from maximum mixed, you cannot get that from expectation. Okay? And in theory, only knowing the expectation means that it could be the case that the state is almost always maximum mixed. And in that case, you can never tell what's the depth because with high probability. So you might think that, okay, expectation does not give you typicality, but what about those concentration inequalities like Chebyshev's? Okay. The thing with those concentration inequalities is that when you try to apply them, you need to show that the variance of the target random variable is small, which means that you want to show that the expectation of the square is very close to the square of expectation. The problem with that is that in reality, they are not really close. In fact, the expectation of square can be exponentially larger than the square of the expectation. And another more important question is that the expectation of square here is already a fourth moment of the random circuit that you try to compute, and it's even for just the second moment, it's already hard, and fourth moment, that's really hard, a really hard task to compute it, and also the computation highly depends on the architecture of the circuit. So our contribution in this work is that we actually managed to prove the typicality result without using all these moment methods. And we prove a specific typicality that characterizes the influence of an input qubit on some output qubits. So formally, let's think of a circuit architecture, an arbitrary circuit architecture, where each gate is independently Haar random. And we look at a specific pair of input and output qubits that are linked by a path of length d, which means that there is a chain of gates that connects this input qubit and the output qubit. And we fix all the other input qubits and try to change that specific input qubit and observe the difference in the output qubit. And what we show is that this difference in the output qubit is always at least 2 to the minus CD fraction of the difference in the input qubits with high probability over the circuit, the randomness in the circuit. So here are some notes about this result. First thing is that this C in the exponent is an absolute constant. It does not depend on the circuit architecture. It does not depend on how you fix the inputs. It is just a constant where the way we proved it, it's, I would say, about 500, but we didn't really try to optimize that part. The second note is that this bound is tight in the sense that you can prove the reverse direction by doing what I just said, by computing the second moment and using the Markov's inequality. The third thing is that by choosing specifically how you fix those other input qubits, you can recover what I said about the single qubit entanglement range 2 entropy. So this typicality this typicality result really covers what I said in the quiz question, that yes, indeed, you can do that, but the proof follows from our result. So the proof of this result is quite complicated, but in order to explain the title, I have to give you a very rough overview of the techniques. So here we try to prove lower bound the ratio of between the difference in the output qubits versus the difference in the input qubits, right? So we decompose that ratio into a product of d different ratios, where each ratio just measures the progress across one single gate. And then we lower bound each ratio by a polynomial function over the entries of that unitary gate. These polynomial functions are actually probabilistic polynomials, and they are very correlated with each other. So in order to prove a lower bound on that, we have to decouple them by proving like a uniform lower bound on the distributions of all these polynomial functions. So here comes the title, the anti-concentration, because intuitively what we are trying to do is to show that all these polynomial functions cannot be concentrated around 0, right? And what we proved is formally the following result, that if you have a degree d polynomial on the entries of a Haar random unitary, then basically the output of that polynomial function cannot be concentrated around 0. In fact, it cannot be concentrated at any constant value, but we only need the fact that it's bounded away from 0 part. And from this anti-concentration bound and plus some calculus, we can get to basically what we proved, the typicality result. So now I'm going to talk about one of the applications of this typicality result that allows us to learn random quantum circuits of logarithmic depth. So to clarify the task here, we have there's an unknown quantum circuit of a fixed architecture, and we are given oracle access to that circuit that we can apply arbitrary input states to that circuit. And we try to output a classical description of the circuit that are functionally close to the actual one. So this task has been studied in the worst case when the circuit, there's no randomness or distribution over the circuit. And the worst case algorithm that the previous works proposed has efficiency that is exponential in the light cone size. So if you think of a brickwork circuit of geometric dimension k, their efficiency is basically 2 to the order of d to the k. The d is the depth, or d to the k plus 1. It depends on what kind of circuit that you output. But in either way, their algorithms are improper in the sense that the circuit that they output will have a blow up in the circuit depth compared to the actual circuit with some factors that depends on which one of the algorithms that you think of. So here, what we showed is that in the case when the circuit C has a distribution that follows where each gate is Haar random, you can actually do that with efficiency just 2 to the order of the depth. So you can learn logarithmic depth circuits, and that is regardless of the geometric dimension of the circuits. And also, the algorithm is proper in the sense that we output exactly the same architecture as the actual circuit. So how we do that is a very simple idea of just try to uncompute the circuit gate by gate. So let's say we try to uncompute the first, some gate G here in the first layer of the circuit. What we do is to try to find the inverse of that gate by just looking through all the possible 2-qubit unitaries. And we apply that unitary before the circuit and feed different input qubits into that unitary, and while fixing all the other input qubits. And then we try to observe an output qubit that has distance d from that input qubit, and we see if we can observe any difference when we fit different input qubits. Right? So if we see no difference, then we claim that basically that is exactly the inverse of the gate that we want to learn. And if we observe some difference that is larger than 2 to the minus CD, then we know that we didn't successfully uncompute that gate. So the reason is that depends on important fact that this output qubit lies exactly on the edge of the light cone of the input qubit, or the event horizon. So in the case that we didn't manage to uncompute the gate, the input circuit will have some influence on the output qubit that we try to observe. And because of the typicality result that we proved, it means that with high probability over the circuit, you will, in fact, observe some difference or some influence of the different input qubits that you feed in, right? But in the case that you actually successfully uncompute the circuit, uncompute the gate, these two gates that you try to apply with the actual gate you want to learn cancels out. And then the light cone of the input qubit shrinks by just 1 qubit, and the qubit that you try to observe now lies outside the light cone. So of course, you will not observe any difference when you feed in different input qubits. So that's basically the algorithm. Okay. And I still have some time, so I will share some thoughts about these results. This project actually started out not thinking about the typicality or the learning algorithm. We started off by thinking what is required or what is the evidence that super logarithmic depth random quantum circuits are pseudo-random unitaries. Because we know, without just the learning algorithm, we already know that logarithmic depth does not give you pseudo-random unitaries. But it seems that above the logarithmic depths, we should have some pseudo-random properties. But what are the proofs or what are the evidence, right? One thing about pseudo-randomness is that if they are pseudo-random, then we know it's hard to learn, right? But then we think, is the reverse true? That is the fact that if we know the circuit ensemble is hard to learn, does it implies that the circuits are pseudo-random? Or in the equivalent sense, if we have some algorithm that can distinguish the circuit ensemble from Haar random unitaries, can we design a learning algorithm from that distinguisher? Okay. So this work is kind of the result, starting from the distinguisher of between the log depth quantum circuits with Haar random unitaries. Because a specific distinguisher that abused that Lycombe property. From that, we designed the learning algorithm, but the general question still remains open because in general, we don't know what the distinguisher looks like. One thing I want to mention is that we know, starting from the assumptions of pseudo-random unitaries, we can have a lot of cryptographic applications. And I want to mention the recent work by my co-authors, Bill and Soumik, that they show that even just starting from the probably weaker assumption that the ensemble is hard to learn already can give you a lot of cryptographic applications. And you can also think of it as an evidence that probably this conjecture that is true, that being pseudo-random is equivalent to being hard to learn. Okay. And that is for my talk. Thank you, and I accept any questions.
We have plenty of time for questions.
Hi, thanks for the nice talk. I was just wondering, how does your work fit relative to the kind of recent stuff on pseudo-random unitaries in very low depth? Like, is the difference just that you consider log n versus, you consider literally log n depth versus they work with poly-log n depth?
So the difference there is that their construction, depending on which construction you're talking about, if you're talking about the construction of pseudo-random unitaries in log depth, they are not really geometrically local, and they don't really have that Lycombe property that we are abusing here. I think the same applies also to their log depth constructions. So I think that's the difference. Here we really need the architecture of brickwork circuit or similar architectures, right? So and another thing is that their construction are not really depending on the each gate is Haar random. They have some specific distributions, and our algorithm actually we need that typicality result that holds for Haar random gates. Yeah.
Thanks.
Hello. So given that local Hamiltonians have light cones coming from Lieb-Robinson bounds, would the algorithm you showed at the end then extend to learning those, maybe term by term?
I'm not really familiar with local Hamiltonians, the theory around local Hamiltonians. So yeah, so I don't really have an answer, but we can discuss afterwards. Yeah.
Okay, thanks.
Yeah, that would probably break the Haar random assumption anyway, right?
Sorry.
Hamiltonians might break the local Haar random assumption.
Yeah, that's what I think, but maybe there's something to do there, but I don't know. Yeah.
I guess I have a question, which is,
Yeah.
it wasn't clear how you learn the architecture from what you presented. You said it's a proper learner and it outputs an architecture, so
Yes.
it doesn't assume what the architecture was.
No, we need to know what it
We need to know it.
Well, we need to know what the architecture is.
Okay.
Yeah.
Okay, I suppose there are no more questions, so we could wrap up, and let's thank everyone again